So next, we'll integrate the second order reaction. For simplicity, we'll use the simplified case of the same reactant. So this is just, I have 2A going to C. Before I do the integration, I want to talk about how the book showed this, how I drew it on the other piece of paper, and then what they actually integrate. Okay? So again, we have rate would be equal to just our basic generic formula. We can write it like this, right? It's changing concentration of A with respect to time. We keep the negative sign there because it's the disappearance of this reactant. We put our stoichiometric coefficient in the bottom. This would be equal to 1 over C dC dt. So we could write this as negative 1/2 dA dt would be equal to positive 1 over 1. The rate of formation of C, we need 2 A's to make every 1 C. So the rate of formation of C is only half as fast as is 2 times as fast as the decay of A. And so you could rewrite this a couple of different ways. You could write, depending on if you change the sign, multiply both sides by -1. You can move the 2 over to the other side. This would be equal to -2 dC dt. It's important to just sort of treat this basic setup as you could do a lot of different things to it, and so long as you're doing the same thing to both sides of your equation, then it's totally valid. And the reason this becomes sort of tricky is that different resources that either I may give you or you may choose to read, or even throughout the textbook itself, if you're sort of following along, how it decides to conceptualize rate is a little bit different. So whether it's talking about appearance of C, loss of A, sometimes it decides not to put the negative sign on because it's saying, what is the loss of the A? And the negative is inherent and it leaves it off because it asked for decrease. So just sort of the thing I just kind of want to draw your attention to is there are a lot of different ways to conceptualize sort of where the stoichiometric coefficient goes, where the negative sign goes. Just be careful as you look at, even throughout your own chapter 15 in the textbook, but other resources that I may recommend. They might just do it a little bit different. So just keep in mind, this is always the overall rate. And we were saying you divide by the stoichiometric coefficients. So you could track any species that was changing and sort of still get the same overall rate. But I'll just say that you can kind of conceptualize rate sort of differently depending on sort of context and what you're asked for. So the rate of the loss of A could be written as K concentration of A times the concentration of A equals Ka squared. And like I said, because I'm asking for the loss, that implies like there's a negative, it's diminishing. And if you were asked for, say, the rate of the appearance of C, then this would be equal to, if you defined the loss of A as Ka squared, then the appearance of C would be 1/2 Ka squared. Okay, so like I said, just maybe be comfortable multiplying all of these equations, different sides of them, to get them into the different forms that different resources are going to use. And so and I'll write one more sort of alternatively. If you define the appearance of C as Ka squared, then the loss of A would be equal to 2K A squared. So just make sure you understand what's going on physically, and then you can multiply things however you wanted. And the reason I bring this up is because what the book previously shows in that sort of molecularity figure is it showed -1/2 dA dt for this reaction here, and it showed like an A and an A colliding. There's a molecularity figure. It's going to show this. It's going to show this drawing. It's going to write this here, -K A squared. And then it's going to go on to integrate this. Okay? It's going to like only keep a negative sign on one side, and it's going to drop the stoichiometric coefficient, and then this is what it's going to integrate for second order. So, and what I will say is that the integration of this is what pretty much every resource uses as its second order integration. Okay? And so this is one where you'll just need to stop and go like, am I being asked for loss of A, formation of C, how much of stuff, everything do I have? Is the negative implied? Who knows? So we'll go ahead and we will integrate that. And that's the version that you'll see most often, and the version that I will put on your equation sheet. So we have dA dt, sort of the loss of A is -K A squared. If we let it be defined, sort of like this, we can rearrange it to 1/A squared dA is equal to -K dt, and we can again integrate both sides, the right-hand side from 0 to t, the left-hand side from some initial concentration to some final concentration. I super botched this integration last time. So when you integrate A to the -2, this would be equal to 1/-2 plus 1 times the concentration of A to the -2 plus 1. This is going to be equal to 1/-1. The concentration of A is raised to the -1. So this is equal to -1/A. And like I said, I just did that like, I don't even know what I did last time. And no one stopped me. And they're like, that's not how you integrate that. I'm like, thanks, guys. Thanks for letting me do it for like 5 minutes wrong. Basically, the problem was I kept the 1/2 on this side and really, really, really wanted to get it to drop out because I knew what the final answer was supposed to be, and I just like couldn't make it happen. And that's when I realized the book was decided to not use that, even though it had kept it originally. Okay. So with this information in hand, if I go ahead and do this integration, I then have -1/A minus -1 over my initial concentration, okay, is equal to -KT. This is then becomes a positive number, so I can sort of rearrange this to 1 over initial concentration minus 1 over my concentration at time t is equal to -KT. And if I move things to the other side, so let's say I want to leave this piece on the left-hand side, 1 over the concentration of A, and I want it to be positive. I now have positive KT plus, I was subtracting this, but it's all going to be positive now, 1 over initial concentration of A. So this is sort of my linear form. Y equals mx. T is my x, K is my slope, I have my intercept, and so if I were to plot time versus 1 over the concentration of A, I would get, this is the linear form for a second. If I want to get a linear plot for a second order reaction, then I would be plotting time versus 1 over concentration. Okay. Or we can get concentration by itself for our reactant, which is the form we've put the 0 in first order in. So 1 over a would be equal to, I'm just going to multiply sort of this a naught throughout. Kt plus 1. And multiply everything by a naught over a naught. Okay. And then if I want to just get a, I can just flip both sides of these. I have initial concentration divided by 1 plus the initial concentration times K times T times time. Okay, and so that's the form where, like I said, it was a little confusing because your book has sort of like a negative 1/2 over here and then like gets to this somehow without explaining what it actually integrated and why. So if you actually plot time in seconds versus concentration of your reactant A in molar, what do you think the shape of this plot looks like? I know, right? I can't look at an equation and definitely know what that plot's like, but let's make a guess. If first order was exponential decay, this looks, it kind of looks like that, like I said, if you plot it, but even faster. We have even more rapid drop off, okay? So second order sort of looks like first order, but with even faster decay. Okay. Same sort of rules apply. This is the direction of the lower K. This would be higher rate constants.